I'm connecting from sunny Los Angeles. It's pretty still dark here. It's early morning. It's 5 a.m., but I'm ready to rock the stage. Hello, everyone. So today we will be talking about the evolution of firmware threats and attacks below the operating system. So a couple thoughts about me. So Marco, thank you for a great introduction. So I'm founder and CEO of Binary. So been 20 plus years in the research and break probably a few times the CPUs and also GPUs. So dedicating my all free time to the surfing. It's one of the reasons why I end up in the sunny Los Angeles, based in Santa Monica. So, all right, let's start with some introduction, what's been in the past and why we have a lot of movements right now on the threat landscape below the operating system. So let's look what is going on from the threat perspective and evolution. We've been always having low level and complex threats from the rootkits perspective, then it's been bootkits. And I think right now it is a huge movement to BIOS and firmware implant in general. So, and this movement happening because we increasing the actual number of mitigations on the operating system level, right? So it's getting more and more complex, it's more mitigations, which is actually easier to break from firmware because it's actually open new opportunities for the attackers in terms of direct memory access and many others. And this growth also actually showing the direction depends on the type of the attacks, also from the hardware and silicon level, right? So basically, just for historical overview, like always endpoint solution, it's been more about like looking on operating system layer, right? So, and checking what is happening in runtime on the operating system, but also, of course, the bootkits kind of force the endpoint solution to look into direction for boot sectors, bootloaders. But hardware and firmware has been kind of like out of scope, right? And developing the solutions for actually be effective for the firmware and hardware-based threats, it's very complicated, specifically if you an agent on operating system level, right? So, and of course, like shifting the threat model, it's kind of like surprising some of the vendors. I mean, they're not ready, and also. If we look from the perspective of the detection of the threats, so this is a screenshot of Moonbound. It is actually another threat which has been discovered in 2020. And this one is very interesting because it's been used 5 years old indicator from hacking team attack. So think about, we have a hacking team implant which has been leaked, right? So, and threat actors like in 2014, right? And it's threat actors still using some of the code from this leak, and this threat been detected in 2020, and basically it's been using the same indicator of infection with FTA invariant variable. Thing is, like this one already been known for actually almost 6 years before this new threat appears. How come we are not detecting it, right? So how come we don't see this indicator which is known? Another one, it's Moonbounds from this year, and it's discovered by Kaspersky Lab. But basically, they said we see this on one of our clients' machine from 2019. But doing the investigation by our team, we discovered this is actually nothing new. It is a Chinese kit which has been used from 2014 for low-level implantation. And basically, the component which is being modified, it's being modified from the platform which has actually been in the market from 2014 May. And it's kind of like a interesting perspective because it shows a very limited way how currently we detecting the threats, but it doesn't mean they are not exist. It means we just don't see them, right? And let's talk about more what's happening right now. why we don't see them, why it's happening in such way which is invisible for security solutions. I wanted to highlight a few interesting issues which has been recently patched by Lenovo in September, and basically this one is very interesting because probably it's one of the first advisories which is highlighting Windows management instrumentation, SMI handler, which has actually been used for setup in the BIOS password. But in 2019 offensive con talk, I've been highlighting like Windows management instrumentation. It's a huge attack surface. I've been showing some of the vectors, how it can be attacked. And actually, as we can see, SMI handler, which is callback function from firmware layer, it's actually being exposed from Windows management instrumentation, right? So basically we can use Visual Basic script to actually trigger the SMI handler from the firmware. This is like actually a very interesting way how you can think about the connection between the operating system layer and the firmware layer from the perspective of kind of like a functionality and how you can open the new attack surfaces. Very, very interesting direction, and basically I think it will be see much more about that. And of course, like it's not only set password, it's a lot of other things, but how you can orchestrate the big network. You can go and manually, as IT security, go and set the password for every user if you have 5,000 users in your network, right? So basically you need some sort of like a scalable way how you can do it, but at the same time, if it is related to security features to the firmware, of course, it's connect functionality from the firmware layer, which need to be used and called from operating system layer. And it's actually exposed a lot of interesting attack surfaces, which is, of course, can cause security troubles, security issues. Another thing, it is a supply chain problem. We've been seeing a lot of different attacks on device vendors, and if you think about on the Taiwanese vendors, it's been constant attacks happening. Like it's been Asus Tech, it's been Gigabyte, it's been others attacked in the previous few years, and also the big device vendors like Intel, AMD, NVIDIA, and Samsung. It's publicly known they've been actually targeted by ransomware or breached by some threat actor which is being in their networks. But also from the perspective of the supply chain, if you think about it, it is kind of complicated how you can guarantee they are not inside your firmware, they not land at the back door, they not been on the server, build server, or like your source code. If they are attack your network, they can also attack one of the developers. And this has caused a lot of interesting thoughts because it's very complicated when such threat actors is actually can attack the silicon vendors, device vendors, and actual third parties, which is developing the firmware for the device vendors. And this happened recently, right? So just like probably 2 weeks ago, we all hear about Adler Lake BIOS source code leaked, but it's leaked because one of OEM device manufacturers like ODM, it's being breached, and actually this one being developing the code for Lenovo firmwares, right? And if you look from the perspective of supply chain, we have a lot of parties involved. And if one layer of this party is being failing and backdoored, so we have the customers which will be affected. It's single point of failure when it's basically include too many parties, which is developing the code, developing the hardware and different components, but it's end up on one party, which is a customer, which is an end user of this device or the firmware, and actually it can cause a lot of security issues, right? So I think it's a lot of good movements happening for actually protecting the supply chain, but thing is, it is actually very complicated problem because a lot of vendors, they basically don't share because of the license or whatever, the source code. You have just a binary. How you can trust the signed binary? Even if you have a SBOM, software bill of materials, which is currently increasing a lot of attention, and it's very good movement, but thing is, if you have implanted firmware, the SBOM will be not show you this dependency, right? Of course, like dependency graphs, it is related to the third-party components, but what if this third-party components been modified maliciously? How you can classify, identify such problems? Of course, SBOM, it's not been created for that. It is a dependency graph to identify all the components which is included in your firmware or whatever piece of software, right? But anyway, it's caused some interesting thoughts about like how we can detect something which is malicious, not only not up to date, or basically contain some malicious code, right? So another thing, like this breach, which has been happening with Adler Lake, it's leaked the platform key from the bootguard, and it's been a lot of paranoia on the Twitter about like this key is leaked. Most of the platforms affected from Lenovo, and nobody actually did the fact checking, and we did the fact checking. We checked most of the platforms which has been in the field and used by our customers, and not only we checked all the firmware which is like device lines been available from Lenovo, and unfortunately we don't find this key. That means this key being not actually on the production devices. Most likely, of course, we don't know for sure for 100%, but our intellectual guess, this key being leaked from some development device, not actual device which is shipped to the customers. Of course, we'll see maybe this device has been not produced yet, or they've been on production line, and these devices will be seen in the future with the leaked key. But basically, to say about all the platforms are affected, it's better to make some validation and checking before blame the vendor. They are actually fact, right? So this is very interesting thing when we get to the point how we can trust our devices, how we can trust the firmware which is coming from the vendors, and what we should do for actual validation of this firmware, what we need to think about our devices, and what the firmwares are more secure, and actually how you can guarantee you don't have implants, right? As example, some of the devices came by default with a compute trace, with a legitimate implant for like a corporate security. Sometimes you can use for like a geolocation tracking your users and a lot of other stuff, but also it can be used in malicious way, right? And we already seen these attacks. For example, LoJack's APT28 been used modified version of compute trace to actually attack the US government. So another thing, it's constant raise of numbers of vulnerabilities, and only by binary, my company, we disclosed like 60 plus vulnerabilities, and also like we still have 50 plus which is under the disclosure. So I mean, that's a lot, guys, and like 95% of these issues are high impact issues. That's mean like it's pretty serious vulnerabilities which has caused a lot of troubles, and what other parties are discovering, right? Why these vulnerabilities are happening, and why all these repeatable failures are not gone, because it's just classical, most of them it's classical memory corruption vulnerabilities. Like I've been finding call-out vulnerabilities like a code execution and system management mode from probably 2013 or even earlier, but basically that's happening again and again. We have some mitigation in place, but how effectively they're used by the vendors and other things, it's caused a lot of troubles. Such number of vulnerabilities, of course, create the mindset this attack surface is very weak and big from the perspective of potential opportunities for the attacker, right? And why I think it is actually happening right now, and we don't see, because like it's just too many things in the firmware which can be used by the attacker and actually affect much effectively the operating system layer compared to other things. Of course, you need to have very comprehensive skills to develop some things, but also like it's been a discussion I think week ago or so about the Black Lotus malware, which is new malware based on UEFI firmware appears, but nobody's seen the sample yet. Interesting thing, but it looks like such movements it's happening on the cyber criminal world too. But it will be interesting to research such malware and see what kind of capabilities been included in there, and not just only speculation, which is currently happening in the media. Anyway, so also after our Black Hat talk in past August in Vegas, we disclosed 6 vulnerabilities to HP, and it's been responsible disclosure, coordinated date of disclosure, and everything else. And in place, what actually everything been coordinated with the vendor. What happened? We figured out a few weeks later. Basically, three high impact vulnerabilities we've been talking about on Black Hat. We disclosed all the details, and some of them actually include the POCs, and our bugs are not patched. Like vendor being aware about these vulnerabilities for a while, and our bugs after the coordinated disclosure are not fixed. And we've been thinking about why is that happening. One of the thoughts, it is also about identification affected, scoping the impact, right? What product lines are affected, what the devices are contained these vulnerabilities. And actually for some of the vendors, it's actually can be a problem. And because they have just too many different product lines and scoping such devices with a forked repository of the firmware, it can be not that easy. And also HP, it's probably one of the firmware vendors which I knew from the UEFI firmware space, which is try to obfuscate their firmwares. They just strip in the names and generate the random ones. Maybe such obscurity doesn't play well when you need to patch the firmwares, who knows, right? And yeah, just come back to Black Hat. We disclosed 12 new vulnerabilities at Black Hat, some of them being a platform initialization phase, pre-UEFI, which is very interesting attack surface. And it's where we will be talking about the future threats and how these movements will be happening. But also just a few weeks ago, we dropped 7 new insight vulnerabilities. And actual next week in Echo Party, it will be another 3 issues, but these 3 issues is actually huge. These 2 new vulnerabilities will be discussed next week. It will be affecting 10 years back of the platforms which is actually in the field. That's kind of like a very, very interesting thing about the firmware vulnerabilities. Sometimes if you find the vulnerability in reference code, or if you find vulnerability in IBV, independent BIOS developer code, it can affect not just single platform, right? It can affect all the vendors which is used this American Megatrends or whatever other IBV code. And then also if it is Intel or AMD reference code, you can actually target all the platforms. And some of the Intel or AMD reference code, it can include a few years back of the devices, which can be also affected by such security issues, right? And this is kind of scary because the firmware attack surface gives so many opportunities to the attacker. And we don't see these threats, but we've seen a lot of vulnerabilities and risk happening. But I mean, it's not true. Unfortunately, like a lot of things which is seen, it's under NDAs, but basically we don't see enough information and risk highlight on the media and publicly, which it creates some sort of like a mindset. It's not happening, but it is happening. So let's talk about pre-UEFI attacker model. And basically, this is very interesting space, because basically what happened in pre-EFI, SMM, it's not initiated yet. It is a pre-DXE mode, and basically it is very, very early after just actual CPU and FSP firmware is passing control to the UEFI firmware, which started with a pre-EFI phase, and it's initiating a lot of functionality, include security features, right? So basically, some of the security features, it just can be bypassed at that phase, which will be never bypassed on the DXE phase from the perspective what you can do from pre-EFI. This is another thing when we're crossing different type of security boundaries, and I think I've been talking a lot about that previously. I think also Christopher Namuni, who is doing a lot of fault injection attacks and side channels, he will be talking later today. He probably also can highlight some of the interesting stuff about crossing security boundaries when you're doing such attacks. And it's exactly why most of them happening, because if you attack at very early phase doing the fault, you can actually cross security boundaries and from different perspectives look on security features which has been not considered. This perspective can be not considered by developers of the security feature, right? But also let's think about NVRAM. What is non-volatile memory means from the attacker perspective? First of all, like because it's used on early boot phase, and by other reasons, it's basically functional reasons. From functional perspective, it's actually not covered by bootguard, and also it's actually created. It exists earlier than bootguard, right? So basically, because it's not validated, any variable which is actually can be modified and cause constant re-exploitation, it can give the attacker the persistent vectors. And that's a very interesting way when you basically don't have any modified components, but you can actually attack the firmware and still gain the persistence effectively, right? And we actually discussed on past Black Hat and previous Black Hat about such of the attacks. We found one of the vulnerabilities, BSSA DFT on Intel reference code presented in 2021 with Alex Tereschkin and Adam Zabrodsky with my NVIDIA colleagues. We worked before I started Binarly. So basically, this is very interesting perspective of NVRAM and how this transition happening between different boot phases, right? But let's talk about how it can be used by the attacker, right? But some note, which is very important, like in many cases, like TPM will not help, right? Because you have the PCRs, which is platform registers, which is used for storing your integrity hash, but this integrity hash will be created but not extended during runtime. That's mean like you will be not affecting after modifications the runtime phase, and remote health attestation in this case will be don't detect runtime exploitation. So it's where we need to create this transition to the future of the attack surfaces and how this is happening. So let's look on this pre-EFI phase. It's been a lot of discussions about the DXE, SMM implants and rootkits. Of course, like it's other spaces where implants can be hidden, but let's just focus on this talk on UEFI firmware, because this is huge. It's easy to exploit from the operating system layer, and it's actually already been used in a lot of offensive operations for many years, which is known. And basically, what happened in the pre-EFI phase is happening too early, right? So we have like no security protections against PyFlash modification in this phase, like BIOS lock enabled, SMM write protection will be not exist. PRX will be not initialized. It's a security registers, which you can block some of the regions to write. Also, Intel BIOS guard are not enabled at this moment. It's exactly what I'm talking about from the security feature perspective. Like, yes, we have all these fancy mitigations, but what if they just not enabled yet, right? So it's kind of like a bypassing by design a lot of the things. And to be honest, the pre-UEFI attack surface from first shootout from the offensive perspective, it's been discussed in our talk 2021 at Black Hat in Vegas, but basically we didn't see like a lot of attention from the vendor side. And when we've been looking at this space, it's a lot of opportunities for the attacker, but also it's a lot of vulnerabilities in there. It's a lot of design problems, which is basically hard to fix. BSSA DFT issue, which I mentioned before from Intel, we can just Google this one. Basically, it is been very long time disclosure process. I would say it's more than a year under the disclosure after we can actually talk about that. And very interesting thing from the supply chain perspective, this vulnerability, it's still on some of the platforms stay unfixed because I don't know why, but it's been no fix delivered from the device vendor, or it is no fix delivered with IBV side, and it's kind of like complicated, and supply chain creating even more problems for the firmware side, which we can imagine. So let's talk from the payload delivery. So I talking from the Keynote perspective, but I want to keep it technical enough and deliver the message from the complexity and the impact perspective to you guys. And look here, so we have like a pre-UEFI phase and the Dixie phase. So operating system will be boots later, but let's just focus on these two phases. And we have like different type, like if you think about UEFI firmware, it's a whole operating system before your main operating system happening. Basically, this is a real-time operating system, which is actually about 6 million plus lines of code, and it's actually bigger than modern CentOS kernel. So it's how complex it is. And also we just cover where from the very high level perspective, the flow, how it can be attacked from exploitation perspective. If you basically have a code execution and platform initialization phase, what kind of like transition phases can be done to survive until SMM and inject code there. And again, like all this, it's crossing a lot of different security boundaries and can just avoid a lot of security mechanisms, which is implemented on Dixie runtime, system management runtime, but it's not initialized yet because pre-UEFI phase is happening too early. So here's a demo from one of our vulnerabilities exploitation in platform initialization phase. I think this one is exactly use BSSA DFT bug, and as you can see, it shows exactly the way how it's hooking different events for keep this transition going. It's actually, this demo exactly show what been described on the previous slide. But let's focus on modern security features. What about platform policy management from new security feature from Intel, and how it's actually can protect our modern devices. This is actually very interesting security feature, because basically we have now not only signed firmware, we have also some checks on which SMM driver need to be loaded, which functionality for all these SMM drivers in terms of the policy need to be applied. And of course, it's controlled by some of the ACM, which is related to TPM, but and the TXT. But basically, another thing we have, it is kind of like, what if we exploit the vulnerability in one SMM driver? Does we still have the full access to the memory region in SMM to affect any other drivers or modify the memory space? That's an interesting question, and let's look together how this feature are worked. So first of all, like this PPAM, it's actually simplify SMA transfer monitor, which is kind of like a Intel developed as a concept back to come back to 2014, 15, when they are kind of like partially open sourced. And the first concept has been very slow. With the time, of course, it's create much more flexibility from the perspective of new security and silicon features. But this one, it's how it looks in reality. Unfortunately, it's not use any sort of virtualization. We have most of the functionality for this PPAM feature implemented still in the firmware, when all the initialization happen mostly in pre-fi phase. But also, as you can see, the policy checking is just one bit, right? So it's basically signaling like true or false if the policy has been checked. What if this bit can be modified? What if the attacker can influence the bit? Does this will be affect this security feature? Basically, this platform assessment model is being created for actually help the device vendors to be more confident. It will be harder to compromise, but from the design perspective, it's actually super complex feature, and it's open new attack surfaces, right? So let's look how basically attack can be done. We presented this PPAM attack on our Black Hat, so more details can be discovered by the link below. But main thing here, like we have a pre-fi. Pre-fi initialized this security feature, and of course it's need to be transition happening, right? So when we have hops, which is hands-on, some basically, let's say, some global variables which is exist during different boot stages, and if this global variable will be signaling something, this can be modified because it's not protected, right? And it's exactly what happened. So this attack being on one of the most recent light books, and we still see this not fixed yet, by the way, in many devices. HP implementation show you basically when it's checking only something exists in the variable, and then boom, of course, it can be modified. Reference implementation is actually different. It is a vendor implementation affected. This bypass, it's not universal. It's focused on HP device, but it doesn't mean other vendors not use the same way, because they need to kind of like simplify for themselves implementation of this feature, because it looks cool on the reference code how Intel want to be implemented, but also how you can scale and support and a lot of other things at the field. It applies to the device vendors, right? So basically, it's more a bit more about this bypass. So basically, as I mentioned, this global data, hop data, it's contain some check for support, like if PPAM should be enabled, and exactly we can modify it. So boom. Another thing I wanted to talk about, it's what we discovered during our Black Hat research. Like, okay, this is security feature, it's platform assessment module, but also if we come back to one of the first slides when I've been talking about that, it's been the certificate, which is stand for attestation. It's kind of like a creating root of trust for this assessment of different modules happening with Intel PPAM. But what we realized, we extract the certificates which is related to this assessment module, and we realized most of them are actually expired. They're kind of like missing validity, but Why? So basically, interesting thing, like a production sign-in key is being expired on all the platforms in the field. Every single platform in the field we are checked. Like, and that's mean attestation is being not enabled for PPAM. And actually, from the attestation standpoint, if we not, like, let's say, if we disable PPAM by the attack previously discussed, so like it will be visible from the device health perspective, from attestation standpoint, but because based on this in context, attestation being never in place for PPAM, so boom, of course, like this attack is very legit, and it's very weird when we have like security feature which is not just configured correctly, not by single vendor, the whole industry. So yeah, it's a bit more details about certificates, how many we checked. As you can see, like we found like almost 200 certificates, which is like 2021, a bit less certificates related to 2020 because this feature is just not being used by majority of the devices in the field, but it's actually been enforced with most recent CPU generation. It's why you've basically seen more recent certificates expired. Right. Why is this all the repeatable failures are happening, and why we still see all these memory corruptions with industry-wide impact? I think, like, first of all, when you have a 6 million lines of code on C language, it actually creates a huge attack surface from any sort of perspective you can imagine. So, like, but of course, some of them can say, oh, we start actually developing some of the firmwares on the Rust code. Yes, that's actually happening. But if you think about from the supply chain perspective, you don't only develop in your firmware component, you need to develop your firmware component on the Rust. You need to develop all these dependencies, third-party components also on Rust. Otherwise, you have like a 20% in the best case on the Rust and 80% of the C code. Still, it's a huge attack surface, and you mitigate probably just 20% of the risk. And of course, like from the perspective of Rust, if you use some unsafe things, like it can cause troubles, as we all can see from the perspective how many issues been found from the Rust standard library, which is using unsafe code for optimization purposes, right? And in general, of course, like save languages, memory save languages are helping to reduce the memory corruption and all these vulnerabilities from that perspective. But like we are still have plenty of space for the logical bugs, for design issues and others, right? We'll see how it goes, and hopefully the industry will be recovered from these repeatable failures. But so far it's happening. Just like shoot out for the most recent issues we discovered. So yeah, I will go a bit faster on that because we have some limited time, and I want to hear the questions. So yeah, this has been presented already on LabsCon, and all the details are available in our advisories. That's why I just shifting. Also, it includes in our blog. So basically, what is most important, how we can remediate these repeatable failures, how basically we can find this automatically. And like my team developed like GIFA Explorer plugin, which is helping to find some classes with get variables and some others. We just start supporting ARM architecture for UEFI firmwares. And funny thing, the vendors already not happy with that. And you will be, and you probably in a couple of months, you will be discover more details when it will be publicly available. So stay tuned. And another thing, like we released some very interesting blog post about how the symbolic execution can apply for actual firmware space from UEFI firmware space perspective. And it's not only limited for UEFI firmware space, this approach, of course. So basically how we are thinking from the perspective of automation of bug hunting in the firmware space, right? You don't need actual device, and fuzzing on the device or basically doing such things on the device, it's not necessary, and also it's limited you on scalability, right? You need will be scaling and depending on the device number of devices available. So like we can do this more effectively, or basically limiting the scope with a potential scope where we are checking. So yeah, it's just some show for detection of SMI handlers, boom, right? Very fast, very effective, and finding the problems. So guys, if you wanted to check your firmware, firmware.run is available for free, but basically community scanner is here. So let's start recovering from these repeatable failures. Don't trust the vendors, check your firmware. And again, as a conclusion, complexity, it's actually an enemy of security. And what we can see, the complexity is just growing. It's opening new attack surfaces. When the attack surfaces are growing, it gives the possibility for the attacker. And talking from the evolution of the threat actors in the firmware space, it's been, of course, always around the firmware and hardware, but it's been mostly happening from the state-sponsored actors' perspective, because they have more budget, they have a more interest in persistent. But now this shift happening actually on the commodity threats, which is coming from the cybercrime attack surface. Why it's happening? Just because the attacks from the firmware get cheaper on operating system. It's not always about persistence. It's actually about the cost efficiency and from the attacker perspective. And this actually happening also, like in general, we have much more documented things, which is increase the knowledge base available, which is researchers did for the years for these attack surfaces. Of course, it's give right now a benefit for the threat actor from that space. Industry definitely need to increase the awareness on the firmware, and specifically on the firmware which is at scale, which is actually executing on the devices. And I hope that will be happen, and this is happening from some of the perspectives, which is enforced by the vendors, enforced by the governments, and enforced by the industry. All this supply chain security things, it's actually help a lot for paying more attention on the firmware, remediate the attack surfaces, and actually reduce the time of response. Thank you very much, NoHatCon, and that's my talk for today, but I open for the questions.